So I've been working on different microcontrollers, and one that I've posted a little bit about was this NXP that I have up and running. I have ordered up PCBs for this TI and Renaissance, and those are en route. And if I scroll down, those boards look something like this for the TI board, and then I have this for the Renaissance board. And hopefully I'll be able to work with those in the next couple of weeks just to kind of see if they're functional and if I can work with the tool set, successfully program them, etc. But one of the things I have worked on in the meantime while I'm kind of waiting for those two PCBs to come in is this Lattice iCE40. Now this isn't an MCU, it's an FPGA, and it was recommended that this might be a fun one to take a look at. So I thought I would do that. And in this blog post, which I'm continually updating, I did put in some content here, and I posted this picture to my YouTube community just saying, okay, I'm starting to kind of work through this, and I got some links to some of the resources that I'm finding helpful, and I'll post more here as I work my way through this. But I'm going to use this iCE40HX4K. It's a 144-pin package that I'll be using. So if I take a look at the datasheet here, if I scroll down, just kind of gives me a quick introduction to what this specific chip is and some details about it, and you can kind of take a look through that. But I'm looking at this HX4K again, and you can see how many logic cells and memory blocks and RAM bits and all this that it has for specs. It does say maximum programmable I/O pins of 95, and if I go down, there is a TQFP, 144-pin TQFP that says 107, and if I understand this right, 14 of which is this LVDS, which I don't know anything about other than the basic concept of it, so maybe at some point I'll get to play with that. But my initial little prototype board that I'm building here, I'm not going to probably get into that. But I picked this specific package, this TQ144, because first of all, it's TQFP, so that I've found to be much better to work with than the, well, BGA. Right now I just really don't have the capability for some of those, just because they are smaller than what I can do with JLC PCB, or they're right on the edge, and I'm just not quite ready to take that dive in and really try to get something like that working. TQFPs I've had good luck with. They seem to be pretty straightforward. But what I looked for was the most I/O pins in a TQFP. Now maybe at some point I could get to where I could run some type of BGA or something like that and get these higher I/O counts. But if I'm sticking with TQFP, I believe this is the highest. It's this 107. So that's what I'm going to work with, and I'll leave BGA for some future endeavor. So then if I go down through this, it of course gives me a bunch of information, and there are a lot of good resources out there, it seems like, YouTube videos, etc. And even on my page here, there was a recommendation to take a look at this little series that John's Basement has on YouTube. So I watched that and definitely would recommend that. Good little series on FPGA using, I think he's actually using this exact same IC here that I'm using. But he walks through the data sheet, so you could definitely take a look at that if you're interested in looking at any of this in more detail. But I've been going through that, and then there's another document that's a hardware checklist. And in this hardware checklist, this isn't as long of a document, but there's some good information about it, like that all the different voltages I need to have supplied, and recommendation for capacitors. And there's definitely some things to pay attention to here. Like here, there are some capacitors that go from a VCC PLL to a ground PLL, but they don't connect into the main ground of the system. They're actually isolated from that. That type of thing here, as I look at that, is something I'm taking into consideration. And, I can kind of keep going down through this, and there's some other, just maybe one thing I haven't done in the design, which I get into, is this power up sequence. So I might have to come back and address that at some point. I'm not doing anything special there, but They do talk about applying power to certain rails and then another rail and then another rail. I'll see, and maybe would look for recommendations on how to time the power up of those rails. I'm not sure how that is typically done. And then there's other considerations in here, and I'll get into some of this. I'll come back to this document, as far as how I'm going to hook it up to some of the pieces of my design here. There's also another document I've been reading through, which is a programming and configuration guide, and then there's also some additional information about specific programming cables. And I actually have, or will be using, I think it's en route here, is this specific programmer. And it has basically the flexibility with these fly wires that I can plug it in however I want. And there's information then on what that breakout looks like. And then if I keep coming down, I believe there's a table that I can take a look at and say, okay, if I've got this programmer, which wires are which color, and if I come down to this specific thing that I'm trying to program, then I can look at, using SPI and which of those wires I'm going to use. And that will show up in the little pin header that I have on the PCB that I'm building. But if I go over to EasyEDA, and I am using EasyEDA Pro for this, I've kind of switched all of my work over to this instead of the EasyEDA Standard. And so far, this is all going well. I'm liking this. But maybe I thought I would just talk through, what do I have here in the design? And any of you that have worked with this, if you catch things that just look off, let me know. And maybe one of the things I will do is I do have this power on sequence for rails. I've got to figure out maybe what that might look like, if that really is absolutely required for what I'm doing here. But I started in the upper left of this, and I have different VCCs here. And so I have a 5.0 volt, a 3.3, a 2.5, and a 1.2. And so my intention is I'll feed the PCB with a 5 volt, and I've made my own little custom component for this Saber connector, so I'll continue to use that. And you'll see that here once I go to the 3D view. But basically, that's where I'm going to bring 5 volt in. I then do have an LDO, and so basically I can regulate and bring out my, in this case, 3.3 volt that comes out, and basically I light up an LED there. So I'll have an LED showing 5 volt, I'll have an LED showing 3.3 volt, and then I also come down to another regulator for getting me to my, this would be my 1.2, and then I have yet another one to the 2.5. And I'm using actually a few different regulators. I probably will try to get more consistent in the future on which ones I use. But some of this are just based on ones I had. And then when I went to actually get this, order up these specific chips, there was a recommended regulator to go with it, and it was just handy, so I grabbed that one. So I've got 3 different ones, and I guess I'll learn about these. I'm hoping they all generally do the same thing, but maybe in the future I'll find the same family of them that just has the different voltages. And I believe there are regulators that have multiple voltages out, so I could probably consolidate some of these at some point. And then I have the main FPGA itself. And there was not a specific component for this in EasyEDA, so I created that. So basically I went in, and in my personal library now, I'm kind of just building up a library of things, but here's this specific component that I created, and so I can see what it looks like, and I even have all the 3D stuff. I did import the 3D rendering of it that I downloaded. But I've got this all set up so that it's laid out pretty much to match the physical layout, which is a style I prefer. I know others like other ways of laying this out, but I thought this was handy. And one thing I've noticed is if I lay it out here in the schematic, when I go to create the PCB, it'll by default pretty much place the components in this same general arrangement that matches the schematic, which wasn't necessarily the default in EasyEDA standard. So I would have to kind of just take everything and get it all moved around and sort that out, but this seems to be much easier to deal with. So I have the FPGA here, and I have all these different decoupling capacitors all over the place. That's what a lot of all of this is. And then I just added basically net labels to pretty much all of these IOs. And so there's a top, there's a bottom, there's a left, and a right. So IO top, IO bottom, that's IoT, IOB, left, right, etc. And I try to just stick with the names of the pins. Now there's a spreadsheet you can download from Lattice that just shows like the full lineup of pin numbers. And then depending on which one you're using, it filters some of them out. So I don't have, one of the BGA chips that has all the pins. I'm using this version that has, half of the total potential pins that this FPGA could have. And that's why some of these, it doesn't seem like it, it necessarily goes consecutively through every single pin number. And I think that's wise. They make their list of names for the full scenario, and this chip is a subset of the full set of pins. And if I went with a smaller package, then of course even some of these would disappear, so it might seem like it jumps even more. From there then, I did come in and add a port for programming, and this is the format of that I am using right now for this little header. So 3 volts on one pin, a bunch of grounds. And then really I've got my SPI, there's the, the select, the clock, the in, the out. So pretty standard, I think. And I'm following one of the standards that's out there. And I've used the same format in some of my other projects at this point now. But that's what I'm going to start with here. I see some other options, but I'll see if this works out or not. So I've got that header set up. I've also come in here and put in some memory. And so I have a serial EEPROM basically that, or serial flash that I can connect in here so that when this boots up, it basically reads from that, the program. At least that's what I understand so far. So that's the way that I'll work with this is I'll program the flash here. And that's what this will actually boot up to. And if I'm way off on any of this, I will find out when I get in and try to actually start working with this. But that is my current understanding. I've got a bunch of jumpers that help me do some configuration options. So when I go to program it, I can either choose to write to basically flash type of data in the FPGA itself. So that's where I'm going to use this actual iCE chip as the target, or I can use the programmer to write to this flash chip. And so I have some jumpers that if I set them one way, it'll write to the flash, and if I set them a different way, it'll write to the chip over here. And I believe some of that writing to the chip is a one-time programming, so you write it once, and it's really meant more for writing to these chips in mass production that's going to go out to, let's say if I had a customer or something I was going to send out a solution to. For me as a hobbyist, I'm going to leverage this flash over here. Got other things in here like resets. There's this done signal, and I think that's when it's done initializing, it starts running. It will turn this LED on if I read that correctly. So I've got that wired in there. Beyond that, I did also come in here and add a few other things. There are some global pins. There's 2 on each side of this package. And typically things like, global clocks that you want to bring in from the outside might come in through one of these. And in that video series, this one down here from John's Basement, he does get in and talk about these global pins and maybe some of the importance of those. I am going to use one of those global pins, and I do have an external oscillator I'm also putting in here. And just to give me a little flexibility, I don't know if I even need this, but I am going to have an option so that I can power the oscillator either with 3.3 or 5 volt. Expectation is I'll use a 3.3 volt oscillator, and then I have a small inline resistor, but if for some reason I don't have the right oscillator, maybe I'll experiment with a 5, and I probably just have to make sure that I don't send into a high of a voltage into one of these pins, but the goal would be to use a 3.3 volt oscillator here. Then I've got a whole bunch of headers, And I did notice as I was going through these, well, first of all, the format I'm using for this is a ground for pins 1 and 2, and then I have 4 signals, and then 2 grounds, 4 signals, 2 grounds. So every signal is right beside a ground when I do hook things up. And this is just kind of a standard format I'm going to use for a lot of these headers. I've actually created these little snap-in boards that basically allow me to just click on top of one of these headers that have LEDs on them. And that way I can quickly test, all the outputs and, turn on LEDs, things like that. The way this is set up is I should be able to rotate this. Even if I put it in one way or the other, it's not really going to matter. It's going to light up the LEDs regardless. So that's kind of the standard format I'm going to use for that. I also put in some memory into this. So if I go maybe real quick, pull this up, but it is a 4 megabit, so half a megabyte, and it is static RAM and 15 nanosecond. I'm not sure if that's going to work well here. I think it should be fine, but I have a bunch of these, so it seemed like that might be an easy thing to just plug in and see if I can't, through the FPGA write to and read back from this RAM, things like that. So that's what this is sitting here for, normal decoupling capacitors, and really just taking the right bank on the FPGA and a little bit of the top bank. So on the top bank, I'm grabbing 8 lines for data, and then all the other lines I'm grabbing from the right bank. Again, that's the right, and then some of these pins up here on the top. And then from there, I also have, just to kind of play around with it, I put in a pair of these TXS 0108s. And these are voltage level shifters, so I can go from the 3.3 volt, which is what I'm using for the I/O voltage, up to a 5 volt, and then I just go to a header. So these 2 headers will be 5 volt headers that I can work with. And actually, I probably have not labeled that on my PCB, so I might benefit from doing that so I don't accidentally plug in a 3.3 something into those headers. This should be a bidirectional. Should be enabled by default, and that's it. Nothing else really set on this. So I'm just connecting it again, in this case, to some of the bits on the lower port, and this is some of the bits on the top port. And then I got some standoffs, and that's about it. So that's the schematic. Now when I go to the PCB version of it, it looks something like this. And I might just go over here and flip to the top layer of this. And I might, just before I forget, so I've got this header, which is going to be 5 volt, and this header is 5 volt. So I'm going to put a note up here. And actually, maybe I'll just draw a box around those so I don't forget that those are a little bit special. Okay, so I'm going to do just a line, top silk screen, make it a little bit thicker, and maybe a tiny little corner radius. No, that's way too much. Something like that. Okay, so I'll do that, and then I will just grab one of these little texts and copy it and put in 5 volt, just so I don't forget. So these 2 are special headers that are the 5 volt headers instead of the normal 3.3. Okay, so I will save that. And if I go back to my schematic for a second, there are pins for the voltage for the I/O, and you'll see that, like here I got just plain old VCC to the chip. The chip runs off of a 1.2 volt, and then here I have an I/O voltage, which is a 3.3. There's also a 2.5 volt in here somewhere, and that has to do with the voltage you needed to write to the internal, like that one-time programming, I believe. So I shouldn't ever need that. I don't intend to use that, but I did hook up the voltage just to have it there. Actually, it's right here. So VPP 2V5, that's my 5 volt connected there. And otherwise, I've got I/O voltage, VCC, I/O, VCC, kind of working its way around. And then there's also these VCC PLL, and that's where I have this not connected to ground, so a couple of decoupling caps and a pull up to my 1.2. And then there's also SPI voltage, which for the SPI, I am going to use 3.3 because I have some other stuff that I think might work well with a 3.3 volt. So the most common thing here is 3.3 volt. The processor, or the FPGA, is going to be on a 1.2 volt. The 3.3 will be used for things like SPI and my I/O 2.5, which I shouldn't ever need, but that's kind of getting that all connected up. Okay, back to then this board. So this is kind of what it looks like, and I've ended up going with, let me go to the copper for a second. So I have 4 copper layers here. So there's a bottom, there's a top, and then the 2 inners. And what I've done is I've actually put a note on the back of the board so I don't forget here. I've put 3.3 volt and ground on the inner plane. So I have full solid inner planes of 3.3 and ground. And then on the very bottom, if I remember the order right, I have 1.2, and on the very top I put a 5 volt. And so basically I've got 2 fills, a lower fill of 1.2, upper fill of 5, a complete inner plane of ground, and a complete inner plane of 3.3. So I don't know if that's a decent way to do this. I'm sure there's much better ways to do this, but that's what I'm going to experiment with here. I do have the size of this board down to what will fit within the low price 4-layer for JLC PCB. And basically that's 100 by 100. So I've got it pretty much 100 wide and 90 tall is where this sits right now. Kind of got this all packed into there. And if I pull up the 3D version of this and just spin around that real quick, let me back up a little bit. So this is this connector that I'm using for all of my power connectors now. And I do have a little enclosure I'm building, and I'll show that later, maybe in a different video. But I use a lot of banana plugs, so I built a little enclosure that takes banana plugs in, and then it comes out of those, out of that enclosure with some of these connectors that I can use to quickly connect in different circuits into this little box that I've built or am building. That little box will also show me voltage and current, and it'll be something that I can set on my workbench so that you can easily see it. It'll face up to the camera so that as I'm working on different things, you can see what voltage I'm providing and how much current maybe something is drawing. This isn't going to draw much for current, but that is something that I am also working on. And those connectors that I'm using, they're these Molex Sabre connectors. So it's a little 2-pin Sabre that I'm using that, kind of looks like this. So it just basically has this nice robust connector. I plug it in, it clicks and locks, and then I've got, a pretty solid connection. This will handle way more power than I'll ever need on any of my projects. And the version I'm using, the 3D model, it doesn't represent it, also has the pins that come through for mounting here. But then, I've got a larger capacitor right there on the 5 volt. And then here's all of those voltage regulators. So I can see with an LED 5 volt, 3.3, 1.2, and 2.5, whether those are powered up and working. Here's my spot for an oscillator so that I can put in, I'm kind of tempted to see if I can't have this generate some VGA signals. So I'll go get the appropriate, I don't remember what it is, 25 point some megahertz or whatever it is that needed to generate a VGA signal, or maybe half of that is workable too. But anyways, I'll get an oscillator that would help me have the right clock to maybe try to do a VGA output on this. And that's where I would just grab some of these pins and run them through a digital analog type of conversion to a VGA type of thing. But I don't know, that's something that if I can get that far, that would be great. But little bit down the road. So here's those level shifters. Here's the spot where my RAM will sit. Here's my little flash chip. I also have an LED indicator for that C done. I've got these 4 basically jumper settings. So if all 3 are left, so the left, left, left here, that means that when I plug into the programming header here, it's going to write to the flash. Or if I put it on the right-hand side, it's going to write to the chip itself. And then really these are just all headers. And you can see I try to label them so I know it's ground, and then this is top 222 and this is left 25A. And I messed up on this header. I didn't want to change it at this point, but I duplicated a pair of these signals. So you'll see 25A twice and 25B twice. So I'll have to see if I actually missed another pair or I just ended up duplicating those unnecessarily. And I'll see what other mistakes I find as I actually get to start working with this. Here's that jumper so I can change the oscillator voltage if I want to go to a 5 volt for some reason. And I don't know if I will do that, but maybe something I can experiment with. You know, this cap up here will probably be like 100 microfarad cap just at the 5 volt. And then really coming into the 5 volt, there's a 10. And then coming out of each of these regulators, there's another 10 microfarad. And then pretty much all the small caps that you see, at least around a lot of these ICs, are going to be a 0.1 microfarad. But then on the back, I've got a bunch of capacitors too to support this chip. So I'll have to go back and look. There's a 0.1 and a 4.7 is what I'm using there. And that's per the documentation that they recommend using those. So that's what I'm using. And maybe there's a couple other things, like a couple of resistors in here and such for pull-ups, pull-downs, whatever it might be. But I tried to get as much packed into the inside of that processor footprint, or FPGA footprint, sorry. And then somewhere a little bit further out. And then up top, the only thing I really put in here was this, the stuff that goes with this C done. And you can see, you know, fill the 5 volt, really just going around the outside of this. The only thing really using 5 volt is if I use 5 volt to the oscillator. Both of these levelers need 5 volt on the upper side of it. And then 5 volt coming into all of these other regulators that come out with the 3.3, 1.2, and 2.5. And then on the bottom was my 1.2 fill. So my 1.2 volt is all this fill. And then, of course, I can come into the middle layers, which are just solid planes for my 3.3 and ground. If I start to split this out, and maybe I'll go 5 here, you can kind of start to see what all the layers are going to be as this board gets manufactured. I thought this was kind of a neat little feature to look at, but I can see what my top layer and really work through the different layers here and see what they're going to look like. And I can spread that out if I want to do that. I did not bother, like with the oscillator. I couldn't find a 3D model for a standard full can oscillator, so I just left it off. And actually, I'll put a socket here, but I could not find a 3D model for the socket or an oscillator. That's why it's just a placeholder. And I didn't take the time to try to find the 3D model for this RAM chip. The RAM chip is, I believe it's an SOJ, so it's got like the curved leads. And that maybe, for me, it was a little bit more of a pain to try to solder than, you know, these other types of formats. But I think that's workable. I just had a bunch of those on hand that I could take advantage of. So I think that's it. As I looked at the price of this, I think it was $7 US to basically get this built up. And actually, I could check that real quick here. So I'll go back to my PCB and I'll go order PCB. Double check my DRC is clear. It is. And we'll just double check what we've got going on here. And I will go back to the DRC information in just a second and show you that as far as what I'm actually using for track size and vias and things like that. Okay, so this came up, and yeah, so $7, and then I'll choose the 3 to 4 day build time, and then the shipping actually won't be $18. It'll just be a few dollars because I'll pick the slow 3-week regular mail option. So for $10, give or take a little bit, I'll get 5 of these boards that I can start working with. If I jump back, I forgot to show the design rules I'm using. So on the design rules, and this is all a little bit different format in the Pro version of EasyEDA, but it seems like I'm kind of figuring it out. There's a spacing section, there's a physics section, but on the spacing, I'm using all really copper 1 ounce, and it defaults to like a 0.102 spacing on the tracks, but then when I go to actually order that through JLC PCB, they don't like it that small and have some extra requirements to do that or cost to do that. So I actually set this up to a 0.152 to space that out. You can see all the other spacing here, but basically for my tracks, that's the spacing for pads, vias, etc. Now, if I was going to use like a 2 ounce, then you can see they default to space that out a little bit more. Now in the actual physics under track, I can go see what is my standard trace going to be, and I bump that down to 0.152 millimeter is what all my normal traces are. The 5 volt I took up to 0.762, and then these others are at a 0.254. And remember, the 3.3 volt, I have a full plane of that, and then the ground, I have a full plane on that. And via size, I'm using a drill of 0.3 millimeter and an outer diameter of 0.4 millimeter. And so I think those are the only ones I've set up. So I've come in here. This is spacing, so I'm looking at spacing for these here. So it's just saying, okay, the spacing on all of these, I'm using the standard copper thickness 1 ounce setting. If I go into the track and look at the physics, that's where I've assigned those rules to make these tracks wider than the default. But all those rules are set up, and the result is what you kind of see here. And so I'll get this and see if I can get the programmer plugged up to this connector here, see if I can get the tool chain up and running, whichever one I think would normally come from this Lattice vendor. And I know there's some other maybe open source ones out there or community projects out there for other tool chains, but I've got to learn all about that yet. And then I'll use those little LED debug headers or debug boards that I can plug into these headers. But as I went through that, if any of you have feedback, if there's something there that you think I am missing or should be thinking about, this is just my first rev, so if I can just make it work, that'll be great. It might be in a future rev I put in a 16-bit memory instead of an 8-bit. I'd love to see if I could make this generate some VGA, and then if I could, maybe even from there, see if I couldn't get some. I've got some different dual port memory, both static and dynamic RAM that I could try experimenting with. I've not done anything with dynamic RAM before, or DRAM, but I have some memory that is parallel in and serial out, and that might be interesting to see if I could generate some VGA signal and manage the DRAM and refresh and all of that type of stuff. But that is currently well above my pay grade, so I will get to learn how to do that if that's possible, and I probably will have questions for some of you that do a lot of this. But that's it for now. Like I said, if you've got thoughts on any of this, let me know, and I appreciate it. Thanks.